So, hello everyone who have decided to tune in live, or for those of you who are again downloading us offline, either through iTunes or Google Play or SoundCloud. Welcome to our next episode. This is our 21st episode in our little podcast here. And as you may have heard, the Nobel was announced yesterday, and as I've been tweeting for the last day or so, the Nobel Prize in topological materials actually does have some intricate and interesting applications when it comes to quantum computing and how we will hopefully build these quantum computing architectures. So take a bit of a look at some of the stuff that I've put online, and hopefully I'm going to see if I can try and get somebody who is a little bit more knowledgeable of how topological materials can relate to quantum computing, but we'll hopefully leave that to a later date. I'm very much doubtful that I'm going to get any of the Nobel winners to come on this podcast, but you never know. But anyway, as for our episode today, I'm delighted to have Daniel Oy from Strathclyde University in Glasgow. So Daniel, thanks for giving me an hour of your time.
Oh, very glad to be here. I mean, just to mention that one of the Nobel Prize winners grew up not very far from here in Bearsden, which is an outer suburb of Glasgow.
Oh, yeah. Is he the one who's at Seattle now? Or is he the one at Princeton?
I can't remember. It's Toulouse, is it?
I'm not sure which one.
Yeah.
I think they're all in America now, but they're all British this time around, aren't they? They just all happen to work in America.
Yes, they're all born in Britain. I think they went to Cambridge, had a news item on Facebook from University of Cambridge saying, congratulations, all three Cambridge alumni.
Yeah, well, Cambridge has had to do that a few times.
Yeah, so there is certainly a local connection here, and it's really good.
Well, wonderful. Hopefully you'll be able to drag him back for a Nobel lecture or something, and use that as an excuse to, I don't know, at least have a couple of free drinks.
Yeah.
So in terms of where you are now, so you and I, just obviously when I disclose when this happens, you and I have worked together on quite a few papers over the years. You're now based in Scotland, in Glasgow, which you have been now for quite a while. Now, quantum has has become quite strong in the Scotland area, whether it's Edinburgh, whether it's Glasgow, or any other universities around. So have a bit of a chat about, first of all, yourself and how you got into this and what stuff you work on, but also sort of the larger community, at least within Scotland.
Yes, it's grown considerably over the time that I've been up in Scotland. I've been here 10 years now. And when I first arrived, there was a community here, but since then it's really grown with lots of efforts springing up around the place. Just shortly after I arrived, together with Elham Kashefi, we started up QuISCO, which is the Quantum Information Scotland Network, basically to try to come up with an interdisciplinary forum for physicists, experimental and theorists to get together with primarily computer scientists, but also people from engineering and mathematics, in order to really develop the community. And we've been having regular meetings over the past decade, and through that, I think that's given the Scottish quantum information community a thread, in order to, upon which that all the development in the area in Scotland has grown. So there are efforts in Glasgow University, there in Strathclyde, of course. In Edinburgh, it's concentrated at Heriot-Watt and Edinburgh in the Informatics Forum, and St Andrews. So those are the main places where the quantum information is. So
basically, two in Glasgow, two in Edinburgh, and one up in St Andrews in Aberdeen.
We don't actually have anyone specific in Aberdeen, unfortunately. There are one or two people who work in related areas, mainly in quantum sensing, but nothing in core quantum information, unfortunately.
So do you span the gambit? I mean, obviously you're a theorist. You and I have done some stuff on architectures and system characterization. Elham's very heavy computer scientist, quantum information theorist. But in terms of sort of these groups, do you sort of span the gambit between, you know, the hardcore device experimentalists all the way through to people like yourself and Elham?
Oh yes. So it goes all the way from actually engaging with industry and as part of the Quantum Technology Hub in Glasgow in quantum enhanced imaging, all the way to you know, stuff that Elham's doing, you know, category theory. I have a colleague in the computer science department here at Strathclyde who works in category theory as applied to quantum information. So you know, from those two extremes, we really span the whole gamut.
So in terms of anything that might have come up recently, I mean, we're going to talk about your latest work specifically a little bit later. But in terms of things that have sort of come out from sort of the quantum community in Glasgow, well, not so much Glasgow, but Scotland, that are of interesting note from your perspective in the last couple of years, is there anything that people may have heard of?
So I'll talk about the hub at Glasgow University. So this is the Quantum Technology Hub in quantum enhanced imaging, and they've taken work that's come out of things like ghost imaging, but also related to that is single pixel imaging, single pixel cameras, and computational imaging, and also quantum enhanced detection, quantum radar, things like that. So,
sorry, just to interrupt, but give us a bit of an idea of what some of these technologies are, because certainly people aren't terribly familiar with terms like ghost imaging and single pixel imaging, and just sort of very rough, obviously.
Well, so I guess it starts with ghost imaging, which is a technique by which you can use correlations between two beams of light. Now, if you have an object by which is maybe sensitive to the radiation that's probing it, then you want to use a very weak probing beam on it. But because it's a weak probing beam, then detectors aren't very sensitive. So what you can do is you can have a what's so-called bucket detector, which basically sits behind the object and basically detects whether a photon or whatever radiation you're using to probe gets past the object and falls onto the bucket detector. Now that single detector or single pixel has no spatial resolution, so it can't actually tell you anything about the shape of the object. Now, if you correlate the radiation which is probing that object in another arm, if you have another a correlated beam, a second beam, which is directed towards an imager which actually has spatial resolution, so for instance, an array of detectors, then by correlating the clicks on the bucket detector with where the correlated light on the second arm fell on the array, then essentially what you've done is you can build up an image of the object with the bucket detector, which has no spatial resolution, but using the spatial resolution in the other arm. And so this general technique is called ghost imaging. There's also a very related technique called interaction-free measurement, which was originally introduced in the context of quantum paradoxes. And so these techniques potentially allow you to do sensing or imaging in completely new ways. So for instance, in this example, perhaps you could reduce the X-ray exposure when imaging a patient. So if you have a weak X-ray source in one arm and a bucket detector to image the patient, and on the other arm you have a stronger beam which can then be imaged by an array, then that may allow you to image with far less radiation dosage, absorbed dosage. So these are the kind of advantages these kind of techniques may give.
So these are active quantum, what I would call active quantum technologies. So they exploit entanglement, they exploit superposition in order to work.
Yes. So this, I mean, there's been a bit of controversy in the community about just how quantum this is. But certainly it's taking the underlying concepts and ideas of correlation in quantum optics in order to perform this. And a lot of interesting work has come out of it. Related to this is the idea of using a single pixel, so having a bucket detector and using a modulated illumination or modulated detection pattern mask, and that can also give you some advantages in acquiring imaging data. I mean, that's not strictly quantum, but it comes out of some of the very fundamental research which has been done in quantum information.
So, I mean, in the context to sort of give people an idea, the quantum imaging is sort of more of a stepping stone technology. It's not as complicated as a full-blown quantum computer or a full-blown quantum communications network, and therefore is expected to be a little bit easier to build, a little bit easier to develop. From your knowledge of quantum computing and quantum communications, you hear a lot of these articles talking about, well, we might be able to get 50 qubits in 2 or 3 years, and we might be able to do some sort of fault-tolerant error correction in 5 or 6 years. Where would you put the technology in this realm in comparison to these other ones? I mean, is it something that you could expect to see coming out commercially much sooner?
Well, so the Glasgow QT hub, I mean, is working with companies at the moment to develop products based on their research. So, in fact, within the next couple of years, you'll see products coming out of the hub. I mean, the first wave won't be fully quantum, but I think that we won't have to wait too long till we actually see actual quantum devices operating, or devices operating on these quantum principles to do this kind of imaging.
Well, I hope so. Certainly, if some people see some kind of quantum technology coming out soon, that will at least convince them that we're not entirely full of rubbish when we talk about this stuff. So in terms more specifically about your work, again, we may as well start off with the most interesting thing that you've been involved with in the past year or so, and this is basically the first launch of quantum technology on a satellite platform. And this is in collaboration with the guys down at Singapore, right?
Yes, so I've had a long-standing collaboration with Alex Ling at the Centre for Quantum Technologies down in the National University of Singapore. And we've been working for years on trying to develop critical parts or critical components of what would go into satellite quantum key distribution, or just basically, if you want to do any sort of quantum technologies or quantum science or entanglement in space, then the real heart of these things are entanglement sources. Produce entangled pairs of photons, and we use that for quantum key distribution, but we can think way beyond that. We can think about setting up a quantum internet using a network, a global network of satellites with these entanglement sources distributing entanglement around the world. So, I mean, that's really the vision that we have in the future of exploiting space for quantum technologies. But we have to start somewhere. We have to start at the very ground level, as it were, and develop the individual components. Now, for a very long time, people have been proposing experiments in space, quantum experiments in space. The initial proposals to do entanglement distribution from the International Space Station, they came out in the early 2000s, but very little progress has been made. Mainly because the funding wasn't there. We had very good proposals, very good scientific cases for doing these kinds of experiments, but they are expensive. Space is very expensive to get into, at least the traditional big space development. So we happened upon a new approach. It was just by accident. I was actually celebrating the 40th anniversary of the moon landings in 2009 at a convention, at a conference in Glasgow. And I just bumped into a professor of mechanical engineering at my same university at this event. And he told me about this new development, which is CubeSats, very small satellites which ride piggyback on big satellite launches. And because they're riding piggyback, they only pay a fraction of the cost of the full launch. Now, a launch of, say, a telecommunication satellite would cost roughly $100 million US dollars. And obviously, we can't afford that kind of thing. We can't afford that. The community can't afford that, right? To just
is $100 million just the launch cost, or is it launch cost plus construction cost?
No, that's just the launch cost.
Right.
All right. We're talking the same amount again for a big satellite. So we're talking orders of $200 million to build a big satellite and launch it. If you construct very small satellites, which weigh only a few kilograms, you can pay a fraction of the cost, maybe a couple $100,000 to launch that, same order of magnitude to actually build it. So for under $1 million, you can build and launch small satellites into orbit and conduct experiments. And this is the approach that we ultimately pursued. So since about 2010, we've been working on building devices, experiments, and now building our own satellites in order to perform these experiments to advance the state of common technologies in space.
So in terms of what you actually did on these two recent papers, the actual CubeSat that you launched, I mean, of course, it's just proof of principle. It's just showing that you can build the components, launch it into orbit for, as you said, a cost that is feasible for academic researchers. But in terms of the actual technology that you demonstrated, what was in the satellite?
So to just explain what the payload was, so the heart of many quantum experiments, quantum computing experiments, is a pair of entangled photons. And usually the method that people use is through down conversion. You take a laser, in this case at 405 nanometers, which is basically what would be in a Blu-ray drive, Blu-ray player. And then you pass that laser beam through a nonlinear crystal. And this crystal down converts the photon. So it takes a photon at 405 nanometers, and it basically produces two daughter photons, which are at, in this case, around 800 nanometers. In this case, it's two different frequencies, so it's non-degenerate down conversion, but they're both traveling in the same direction. And these two photons, if you arrange your apparatus correctly, these two photons are entangled. In this case, we use the polarization degree to do the entanglement. And so normally, at the very beginning, these devices took up a whole optics table. And basically, you can't launch an optics table into space. No. And even more difficult is launching the PhD students up with the optics table to tweak it, to make it work. So a lot of the work has been done in order to take what is several hundred kilograms and several cubic meters and shrink it down to the volume of 300 grams and 300 milliliters. So basically the volume of a can of Coke. And we need to use very little power, a couple, maybe a watt or two, and it must be rugged. It must be able to survive the launch. It must be able to survive radiation. It must be able to survive the vacuum and also the thermal fluctuations. A satellite in low Earth orbit will go in and out of the shadow several times a day, and consequently the temperature will go up and down inside that satellite. If a laboratory experiment, they try to stabilize everything to within a degree environmentally, and they may use other things like coolers or heaters in order to maintain sub 1 degree temperature stability. We don't have that luxury. So in order to do this, you have to turn what is a science experiment into something which basically you can give to the launch company, send it up, and it has to work without you actually being able to be up there tweaking it. And so that was the primary challenge to do so. And so what is up there at the moment is what's called a correlated photon source. So it's basically the source that we've been developing to produce entangled photons, but We haven't inserted all of the crystals required in order to produce a fully polarization entangled source. I mean, the photons themselves, they actually are entangled because they're entangled in the frequency and momentum and time. But those aren't the degrees of freedom that we're actively exploiting at the moment. So we call it a correlated photon source, even though there is entanglement, but we don't actually exploit that at the moment. So the experiment at the moment is to basically check that the basic design works, and it is working very well. It's producing highly correlated photons. The polarization analyzers, in order to check that the source is actually producing these correlated photons, is working very well. And we're monitoring things like the radiation damage to the single photon detectors, which we use to detect the correlations. And this is all giving us very valuable data about what the next mission will be like.
So it's still, I mean, it's been continuously transmitting data ever since you sent it up. You're still analyzing stuff that's coming down now.
Well, it's sort of like we're like the flea on the rat on the cat, right? In that our experiment is only a payload upon a bigger satellite, this CubeSat, which is run by the engineering department at National University of Singapore, and they're running other experiments as well. So we have to timeshare.
Okay. This was going to be my next question, because I'm completely unfamiliar with these CubeSat ideas. Obviously, when you say piggyback on a launch, I figured it was piggybacked on a launch, but then sent off independently. So you actually had your own communication system.
Yeah, it is.
Oh, it is.
So it is. I mean, literally, it's about this big. That's the satellite. It's freely floating in space. But within this, we have our own experiment, and we have to timeshare with other experiments in this. So this satellite isn't just doing one experiment. Our experiment is doing other people's experiments as well.
Oh, okay. So this is why you said you can have a couple of kilos in your payload, but yours has to be only 300 grams.
Yes.
Ah, okay.
The whole thing weighs about 2 kilograms. And so, so 300 grams is our bit, but then there are going to be other payloads which are about the same order. So I can't remember exactly how many other payloads they've got, but we have to timeshare. So we have to share power, we have to share communications. So it's run periodically, and basically we want to build up a time series of its performance. Over as long as it's up there, and that should be a couple of years, hopefully.
So how's its stability so far? I mean, it's still obviously working.
Oh yes, well, I mean, the performance is actually quite interesting in that we found that, for instance, the polarization polarization correlations actually are still very good. They haven't degraded. We don't see any signs of that degrading. The liquid crystal polarization rotators that we used, which the people who make them and other people use them told us that no, radiation will destroy them very rapidly, and you'll never be able to use them properly. They have actually held up very well. So actually this in-orbit validation of its performance has actually shown us that this approach will work very well. The most critical part of this experiment is the single photon detector. So what we need to do is we need to measure the polarization, and that's done by using polarizers and polarizing beam splitters, and ultimately detected by single photon avalanche photodiodes. And they're very sensitive to radiation damage. So as it's exposed to both gamma rays and electrons and proton bombardment, then they cause damage to the actual silicon in the diode, and that causes the dark count rate to go up. So that means that if there's no photon arriving, it will still give click and give an error, an erroneous result. And we've been monitoring that from what we've measured prior to launch, and then we've seen a gradual increase in the number of dart counts that we get, the dart count rate. And it's interesting because it's higher, the radiation damage rate is higher than our models predicted. So before we actually think that we actually used industry or industry models or models which are well, I don't know, respected, but basically generally used, widely used to predict what radiation you should expect in space at that altitude and the various orbital conditions, and use that. And we did some prior radiation testing, so we actually took our devices, put them in front of gamma ray sources, or put them in front of a cyclotron or a synchrotron, and exposed them to actual radiation and measured the performance at the various radiation doses. So we were able to compare our models and the actual ground data, and then predict what we should expect in terms of the start count rate increase. And we found that the models seem to have underestimated the amount of radiation that they should receive at this orbit at this time of year. So, you know, where it just proves that you can do all the modeling, all of the design, all the calculations you like on the ground, but when you get it into space, that's really the taste of the pudding.
So, I mean, in terms of the data that you are getting, obviously classical communication satellites have, you know, lifetimes that range into the decades level. But in this case, because obviously it's quantum technology, it's extremely sensitive to environmental errors. And as you say, each component has its own quantum behavior that gets easily damaged by these things. What's the challenge now? I mean, does it really, we now have to, if we're going to start putting this technology into space, we're going to have to think of some very different material science rather than just, you know, we don't have these concerns if we were to say build a quantum computer on the ground.
Yes, no, I mean, this is exactly correct. I mean, they say, you know, this is rocket science, and the reason why they call it rocket science has a reputation for being difficult is because it is difficult, because it is a very harsh and challenging environment. The way you get into space is insane, really, compared to every other method of transportation. Sending a rocket into orbit is a massive event. You know, nowadays we take it for granted, but every so often, you know, maybe 1 in 10, 1 in 20 launches, it blows up.
Well, we all saw the SpaceX one from a couple of weeks ago.
And that was even before they were launched it. That was testing stage. So it just shows you how challenging and difficult just even getting into space is. And to put it into perspective, we had a setback. So in 2014, in October, we had our first planned launch of our experiment to space on the Antares launch. It survived a total of about 30 seconds from launch until the launch vehicle exploded in a ball of flames and crashed down on the launch pad. And that was a bit of a gut wrench to see your experiment not even make it 100 meters or 200 meters above the ground. The interesting thing is that later on they actually recovered the capsule which contained the satellite, and they returned it to the satellite manufacturer. This is Gomex. It's a company out of Denmark, which was hosting our experiment. And it was slightly bent, the satellite, but they plugged it in and it turned on. And the experiment was in fully working order.
Really?
And so we were actually able to run, diagnostic tests and actually run, compare the results before and after it survived what we call a rapid unintended disassembly event.
Oh, please tell me that's in a technical paper somewhere.
It is. So actually, Alex, my collaborator, has published the paper on extreme environmental testing of quantum devices, and so we have to build them rugged. We have to build them to survive launch, but in this case, we built them. They were able to build it to survive an explosion. So this is just even before we get to space.
So, I mean, the next step, I mean, you said that this experiment's going to inform what you and the guys in Singapore are going to design for the next generation of payload. In the meantime, there has been this Chinese launch of a similar quantum satellite. So what have they done compared to what you did with the first launch? And then has this sort of changed your mind as to where you guys are going to go next?
Well, I just think that you know, what China has been able to do, what Dr. Pan has done, has been absolutely amazing. Be able to do a lot of the preparatory work. You know, there's a lot of development work that has to be done before you even consider launching that kind of experiment. So to explain the difference between what they've done and what we've done, I mean, we're operating on a shoestring budget, and we've been concentrating on getting, you know, the entanglement source or the components required for entanglement source working in space. They've gone the full hog, right? They're going to do full quantum communication from space to ground. So they want to send single photons, entangled photons from their satellite to ground receiving stations. Everything that we do in our satellite experiment happens on board satellite, because in order to do the actual transmission, you need a bigger satellite, you need a more expensive satellite, you need much more components that need to be developed. So I mean, in comparison, their satellite weighs 640 kilograms or 650 kilograms.
So they did launch an optics bench into space.
Yes, they launched. Actually, they've launched several pieces of equipment into space, and you know, you can sort of estimate how much they've spent on this. You know, order of $100 million on the satellite itself, plus the launch cost, but it's done through the state, so it doesn't cost them anything. Really.
They're not piggybacking on anything. This is a dedicated satellite for this experiment.
That's a dedicated launch. So if you include the launch of a dedicated launch vehicle as well as a 640 kilogram satellite, plus all the massive development we've done. What we're doing is we're trying to you know, advance in very small steps, and they've done the big leap. You know, they've gone directly to a big satellite and the full transmission experiment. Our next launch will be possibly next year, and that will be to test an upgraded version of the experiment that we've already tested in space, and that will be a fully entangled source, and it will test improvements. It will test improved detectors, perhaps with the radiation shielding, you know, revised circuitry, all that kind of thing. So we take the lessons learned from the first mission, we iterate it, do a second mission, learn more, and then there's a plan for a third launch, possibly 2019, where we have an even more improved, high brightness, more rugged design. So we're taking these small, rapid, well, comparatively rapid steps compared to putting all our eggs in one basket and going for the big mission. It means that, you know, the investment is smaller at each stage, that we de-risk it. That means at each stage we've eliminated or we've mitigated against risks of the previous mission, and then we can develop improved components or improved designs for the next one. And in this way, small teams like us can actually contribute to this endeavor to putting space technologies into orbit.
So who's in this space at the moment? I mean, obviously the Chinese and you guys are doing it. The Viennese, the Zeilinger and Rupert Urson and people like that in Vienna had been talking about, as you said earlier, putting these things on the International Space Station, but that hasn't, you know, eventuated yet. Is there anyone else except you guys and the Chinese at this point that have, you know, really gotten to the point of actually sending stuff up there?
I mean, there's quite a few groups around the world working in this area. So you mentioned Anton's group and Rupert. So they're collaborating with the Chinese, with Pan on this, and hopefully they'll be receiving entangled photons from the satellite also maybe to generate QK links between China and Austria. They obviously have their own efforts, and they're working with people like ESA, European Space Agency, developing other components and things like that. There's the people like Paolo Vizoresi in Italy, who are doing experiments testing the optical link properties between space and ground using retroreflectors of satellites. They send it in weak laser pulses to satellites and then observing the very faint reflection back and testing the quantum properties of that channel. Very impressive work there. There are people who are actually doing following a slightly different approach to satellite quantum key distribution. Most of the people are using discrete variable quantum key distribution, so either polarization or some proposals to use time bin entangled photons for doing quantum key distribution. There's another approach based on continuous variables, or CVQKD, and so this is an approach that the group of Gerd Loix and Dominic Elsa are taking, and they're using, actually very interestingly, modified conventional optical communication terminals. So they've got these basically they're mini telescopes on gimbals which attach on a much bigger satellite. So for instance, if you have a telecommunications other big satellite, you can slap one of these optical communication terminals on it, and you can use that in order to do high-speed data transfer from orbit to ground using a laser signal. And so in continuous variables basically use a very attenuated laser, and you encode information into the continuous variable degrees of freedom, the quadratures, for instance, and you modulate those, and then you receive them and you demodulate it, for instance, using homodyne detection, and that gives you a alternative way of generating secure keys using what is essentially just a modified conventional classical communication device. So that's one approach. More conventionally, there's the group of Thomas Genevine at Waterloo, and they've been pursuing both conventional satellites, but also CubeSats, similar approach to what we are doing in order to perform experiments. And they've been doing a lot of development work in developing the transmission equipment and receiver equipment. Their approach differs slightly in that they want to leave the source, either a weak coherent pulse source or entangled source, on the ground, and only put the receiver on the satellite. And so they put the polarization analyzers on the satellite, and they send up the single photons. So that's different to what most other people are doing, where they put the actual source on the satellite and then only have the receiver on the ground, and they just use a telescope to receive that. So there are very many different approaches and ways that people are attempting to develop this technology, and I think it's really good.
Do you think that I mean, there was always, because I've done a bit of work with quantum repeaters and other methods for quantum networking, and there's always this fight between people, especially on the quantum, the ground-based stuff versus the satellite-based stuff. Given your familiarity with the satellite-based stuff and the fact that we have our own problems in quantum repeaters, especially not so much for QKD, but for much more in the future when we're talking about an actual quantum internet connecting things.
Yeah, repeaters are swapping things like that in order to.
Yeah, and repeaters can be error corrected, or at least in principle they can be error corrected. They're basically mini quantum computers. I suppose you could do the same thing with satellites. But you're then shipping mini quantum computers into space. The obvious upside to satellites is that you can, in principle, get much longer distances in one hop.
Yes. I mean, so that is one of the drivers for developing this technology, specifically for QKD purposes. We know that fiber-based systems without development of repeaters, quantum repeaters, is restricted to of the order of 100 kilometers, maybe 200 kilometers. I think the record at the moment is like 300 kilometers, but practically you really are talking about 100 kilometers to get the key rates that you need. So if you want to span continents, then either we have repeaters, quantum repeaters, and have them spaced every 100 kilometers. So to go across the Atlantic, I don't know how many you need.
They're full quantum repeaters. Unfortunately, they've got to be a lot denser than that. You're talking closer to 10 kilometers.
10 kilometers. So let's say that we want to. So we're talking hundreds across the Atlantic, and you have to get to the bottom of the ocean. So it's the question is whether that technical development. What's the cost of doing that compared to a single satellite distributing entangled pairs between London and New York? And the rate may be slow, but at least you're getting pairs. Whereas there's no way without repeaters to do it in a fiber-based network. So at least in the near term or the nearish term, long-distance entanglement distribution, I think satellite-based networks definitely have a role to play. And there aren't any real showstoppers preventing that. We know how we can do it. We just need to be able to develop these stabilized satellite platforms with large enough transmission apertures which can point accurately enough, and the ground station technology is basically there already. And so the question is, how big does a satellite need to be in order to simultaneously transmit pairs of entangled photons to two different ground stations separated by 1,000, 2,000 kilometers? And I think we're getting there. Yeah.
Well, I imagine it's, I always talk about, quantum computers mirroring classical computers in their development. Well, when we're talking about quantum communications mirroring classical communications, the 40s and 50s, it was all satellite-based. And then we decided that, we needed higher and higher speeds and higher rates, and optic fibers were developed and they were refined, and then everything started being pulled back down again.
I know. I mean, I see them as complementary technologies, because even today, satellite connection, satellite communication coexists with fiber-based communication. If you're in the middle of the country, you're in a remote mining station sending back data to head office, there may not be an optical fiber link that you can use, but say it's for instance, if you do exploratory mining and you need to say that there's how many, what resources are, resource information there, which is highly confidential and worth millions of dollars, you may want to use a satellite QKD link in order to secure that information, but you don't have access to a fiber optic network. So there are situations and cases where they can complement each other. Obviously, within a city, intra-city links, they're going to be fiber-based. Maybe cities which are separated by tens or 100 kilometers, fiber-based networks are definitely the way to go. But at least in the short term, if we want to span long distances or places which don't have existing fiber infrastructure, then satellites have a role to play.
So, I mean, we're going to talk about some other stuff, but we've nearly exhausted all of our time just talking about this. But I mean, this is very interesting. I'm sure it's very interesting to anyone else who's listening too. This kind of stuff actually going up. But the one little thing I did want to ask before we just get into some more general stuff and start to wrap this up is that in the computational space, we are starting to see a much more active role being played within the private sector, whether it's Google, IBM. The CBA in Australia and Telstra in Australia have invested heavily in the silicon work. Now, you've talked about the Chinese investment being very large, but obviously that's coming from the state.
Government,
it's not coming from private sectors. In terms of your work at NUS and in Glasgow and the work of the Vietnamese and the Europeans, has industry started to come in this, or is this pretty much still an exclusive realm of government and universities?
I mean, I think for the terrestrial stuff, we've seen that investment already. So the quantum communications hub, quantum technology hub in York, they have a lot of industry engagement. You know, the large, say, the electronics companies. You know, in the UK, you know, BT, British Telecom, is heavily involved in investing on the terrestrial front. But in terms of satellite QKD, one of the effects of the launch of the Chinese quantum satellite has been a resurgence of interest amongst commercial companies, and you know, I think, you know, they are calculating their response. They need to keep on top of these developments, and I have been engaging with companies both on, say, the downstream sector like BT, or the upstream sector, companies like Airbus or Thales. So you know, these companies, they definitely are keeping a very close eye on this, and I mean, I think at this stage we're still at the, you know, what we call low technological readiness levels in terms of satellite QKD, and companies would like to see that raised a bit before they can really see a route to market or a route to implementation, commercial deployment. And a lot of the effort at the moment that I'm particularly involved in is in order to make that leap from, you know, the low TRLs into the mid TRL level, where companies then can see that direct route. And you know, it's an interesting time, because, you know, you're looking at turning what were laboratory experiments or scientific experiments into something which really is a technology, something that has to be robust, deployable, economic. And yeah, I think once we reach that stage where there is this clear vision of how it's going to develop, then I think the commercial companies are going to really jump on board.
Well, it has been an explosion in the last 18 months to 2 years across, you know, a huge swath of the quantum technology sector. So I think it's inevitable. So we're basically hitting 50 minutes now, and then usually, as I said, I try to keep these things to 45 minutes or so, so that we don't overwhelm people. But just to, as I usually do for everyone who comes on these podcasts, is there anything interesting happening, anything you want to plug, opportunities available, either within your collaboration with NUS or in Scotland itself?
I mean, one of the great things about this, the community, that, you know, the satellite QKD community, is that, you know, generally it's been very open and very open to collaborations, and we all see, you know, this challenge as something that we can't all just do by ourselves, and so we're very open to collaboration. My collaborator Alex Ling, you know, we're looking for people who are very interested in developing other aspects of a QKD system for satellite QKD technologies. So you know, if you think, you know, there's a project or an experimental mission that you know, that possibly could use a very compact, very robust, explosion-tested you know, entanglement source for your experiment, then just drop us a line, and we'll be very happy to discuss.
Well, as usual, I will definitely put in all the contact information, both in the description on the YouTube channel and to our other distribution platforms for the podcast. So yeah, as Daniel said, if you can think of some good ideas, and send them an email, send them a tweet, send them whatever, and trying to get into contact with them, and I'm sure they'll be incredibly enthusiastic to talk to anybody. So that's it for our episode today. So once again, I'd like to thank Daniel Loy from Strathclyde and Glasgow for sitting down with us and having a great chat.
Yep, thank you, Simon, for inviting me.
No problem at all. So this will be uploaded, obviously, to our other accounts before the end of the night. I'll do it before I go to bed. Next conversation is hopefully going to be with the co-founder of 1QBit. That's still yet to be finalized exactly. This one will be an offline conversation. We won't be doing it live on YouTube, but when it's ready, it will be uploaded to YouTube and our other accounts. But again, stay in line with us. Follow us on Twitter and our other social media accounts for updates and schedules of our next episodes. So thanks all of you again for joining either live or offline. Thanks again.